Welcome to Chapter 15. We're back with the proof of a conjecture from Chapter 12 on Balanced Squircle Scales. The conjecture we'll be starting with is the Balanced P cardinality conjecture, which just says that the amount of balanced P greater than or equal to 1 is finite. We'll start this proof by reworking some notation to remove some ambiguity when it comes to mod. From now on, this mod will always refer to the equivalence relation congruence mod n. But this mod will be defined as a function that returns the smallest positive equivalence class of the input value a mod n. In other words, mod of an will subtract an integer multiple of n from a such that the result is greater than or equal to 0 and less than n. So instead of this notation derived from the sum of delta base p's, we'll use this instead. Let's take this summation of arc mod 12 on the right. Let an be 42 over pi arc base p of pi over 6n, and let kn be floor an over 12. Of course, we can replace the arc here with ai, but we can go further by the definition of kn and mod to turn the summand into ai minus 12 ki. We can split the sum, and finally define big K as the sum of these little k's. Recall the definition of balanced P from Chapter 12 and how we can rewrite it like this. Using our substitutions from the previous slide, we can rewrite our equation like this. We'll move the 12k to the other side, and now we're going to do a little replacement. Since k actually changes depending on the value of p, the equation we have now is saying something about a specific balanced p value. In order to solve for properties of any balanced p value, we'll replace k with some natural number n. A consequence of this is that now we're not just solving for balanced p, but for when the delta sum is equal to any integer multiple of 12. In other words, squircle scales that are offset by any number of octaves. It might be easier to understand changing the k to the n when stated like this. This sum being equal to 12m for some integer m implies that this sum equals 12n for some natural number n. Anyway, let's continue. Using the weak decomposition formula from Chapter 12, we can completely get rid of this summation. We'll clean up this expression and take another moment to understand something. Arc base 1 of pi over 2 is the shortest distance between 1, 0 and 0, 1. It's the only squircle with this arc length at pi over 2, and it's a local minimum. Geometrically, we can see that as we increase the value of p, this arc length only increases. So the derivative of arc base p of pi over 2 with respect to p is always positive for p greater than or equal to 1. Additionally, we can see that this arc length approaches 2 as p approaches infinity. Just taking into account p greater than or equal to 1, we know that arc base p of pi over 2 is between these arc lengths. Let's replace them with their actual values and just edit this expression, treating it like an inequality. The key here is that since we know that arc base p of pi over 2 is strictly increasing, it only hits each of these values inside the interval once. In addition to that, we know that since there's a horizontal asymptote, that this equation can only be true for a finite number of n. But to be absolutely certain, we can find out exactly how many natural numbers that is. First, we'll take the difference between the endpoints of this interval, which is about 172. If we take this value, divide it by 12, and then floor it, we'll get the maximum number of times that arc base p of pi over 2 passes a multiple of 12 on the interval, which is 14. We can verify that with this inequality, and so there's an upper limit of 14 balanced p. We could be finished here, slap a QED on it and call it a day, but since there are such a small amount of possible values, let's just find all the balanced p greater than or equal to 1. And here they are! There are 9 balanced p values. I did miss a balanced p value when reciting them in Chapter 12, so that's 3.6482. And while we're at it, the other 5 values that have offsets of multiples of octaves are these, and here are the corresponding delta sums. Interestingly, this shows that there is only one p-value greater than 1, such that its delta sum is an octave down, as p equals 5.5101. But either way, there we have it, the balanced p cardinality theorem. There are 9 balanced p-values. We do have one more thing though. Since in our proof of the balanced p cardinality theorem, we showed that a p being balanced implies that this equation is true, we can use that to prove our other conjecture from chapter 12. We'll use linearity at pi over 4 to turn this pi over 2 into a 2 pi, divide both sides by 3, move the 22 to the other side, isolate the arc term, do a little factor, let k equal n plus 5, and we get that p being balanced implies that the circumference of the squircle is of the form 2 pi times 2k plus 1 over 77 for some natural number k. So goodbye balanced p circumference conjecture, and goodbye balanced p rational circumference theorem, and hello balanced p circumference theorem. So there we have it. Balanced p cardinality theorem and balanced p circumference theorem. Yay! Okay, bye.